I'm Professor Rad, and in this video we'll be talking about rotations and reflections in R2 using linear transformations. So we're going to start out with a note, kind of defining some special matrices, and then we'll work our way through a few examples. So in the note that I have over here on the side, here are some special linear operators. Now remember, the difference between a linear operator and a linear transformation is just that a linear operator is a special linear transformation where its starting space and ending space are the same spaces. So we're starting in R2 and then we're going to R2. So the first special type is if we do a counterclockwise rotation through an angle theta. So think about taking a vector in R2. So I got to turn around for this. We're living in R2, we've got this vector, and then we're going to rotate it through a certain angle, right? So we're rotating counterclockwise through the angle. Then we also have a reflection over the line y equals mx, so a line running through the origin. So if we have line y equals 2x going up like this, then we're reflecting over that line for our vector. So this is the matrix that's going to induce that reflection. So in the future, pretty much towards the end of this section on linear transformations, we'll be talking about how you can find matrices kind of like this. But for right now, we're just going to apply them and see what we get. So in example 7, we have two linear transformations or linear operators. T is going to rotate a vector in R2 through the angle of pi thirds, and S is going to reflect a vector in R2 over the line y equals negative 2x. And they want us to state the matrices that induce each of these transformations. So all we're going to do, we're going to treat this kind of like a formula, plug in and simplify. So for, let's do T first. For T, T rotates through the angle pi thirds. So we're going to replace theta here with pi thirds. So we're going to have cosine of pi over 3 and sine of pi over 3. Negative sine of pi over 3, and then cosine of pi over 3. Now, pi thirds is one of those angles we're supposed to know. It always helps me to draw a little mini unit circle for reference. So pi thirds will take me up here. So the y value is taller than the x value is wide. So this means we've got 1/2 and root 3 over 2. So that means our cosine value will be 1/2 and our sine value will be root 3 over 2. So this is going to be 1/2 negative root 3 over 2, root 3 over 2, and 1/2. Here we go. All right, so let's take a look at S then. So S is reflecting a vector over the line y equals negative 2x. So this is our formula here, where m is that slope. So we're going to start out with 1 over m squared plus 1. And here m is negative 2. Then we have 1 minus m squared. 2 times m. Again, 2 times m. And then we have m squared minus 1. All right, so let's go ahead and simplify these a little bit. So negative 2 squared is 4 plus 1 is 5. So we get 1/5 times. We get 1 minus 4, which is negative 3. 2 times negative 2, which is a negative 4. And 4 minus 1, which is a positive 3. So we end up getting negative 3/5, negative 4/5, negative 4/5, and 3/5. So there we go. This would be our final answer here. So this is the matrix that is inducing that reflection over the line y equals negative 2x. And then this matrix would be our answer for T. This is the matrix that is inducing the rotation through pi thirds. All right, so now let's look at an example of applying these transformations to create a new one. Alrighty, so For example 8, we're supposing we have a linear transformation that does two things. First, the linear transformation is going to reflect a vector over the line y equals negative 2x, and then it's going to take whatever result we get and reflect it through the angle of pi thirds. And we want to find a matrix that's going to induce this linear transformation. So these two things that this linear transformation is doing is a combination of the two transformations we just looked at. So we had t, so I've called this matrix A sub t because this is the matrix that induced t. And then this one is AS, this is the matrix that induced S. So let's work through what this transformation does and see if we can come up with a matrix to induce it. So first, it's going to take a vector in R2, so I'm just going to call that xy, and it's going to reflect it over negative 2x. So that was this matrix here. So let's put that vector xy through its paces and multiply it by this matrix. So we're going to take negative 3/5, negative 4/5, negative 4/5, 3/5, and we're going to multiply that by the vector xy to see where this vector is going to get sent to. So this is going to send it to negative 3/5 x minus 4/5 y. So negative 3/5 x minus 4/5 y. And then we have negative 4/5 x plus 3/5 y. So negative 4/5 x plus 3/5 y. So the first step of this new linear transformation is to take our vector xy and turn it into this one. Then we're going to take this answer and rotate it through pi thirds. So now we're going to take this matrix and we're going to multiply it by this one on the left because this is the result that we got. So we're going to take 1/2 root 3 over 2 negative root 3 over 2 1/2 times this result. Negative 3/5 x minus 4/5 y minus 4/5 x plus 3/5 y. Sorry about my squeaky marker today. Okay, so let's multiply these out. So we're going to get 1/2 times this top minus root 3 over 2 times this bottom here. So I'll write it out down here just so I have more space. So we have 1/2 times the top, negative 3/5 x minus 4/5 y, minus root 3 over 2 times the bottom, which is negative 4/5 x plus 3/5 y. Okay. Then this one times the top, and then 1/2 times the bottom. So we're going to get root 3 over 2 times negative 3/5 x minus 4/5 y plus 1/2 times the second one. So negative 4/5 x plus 3/5 y. Cool, this only looks like a small disaster, right? We can plow through it. I have confidence in us. So let's go ahead and combine our like terms. Now, one thing I'm noticing is that everything's going to end up being divided by 10, basically, right? Because this 1/2 times these fifths is going to result in tenths. So I'm going to factor out a tenth so I don't have to keep writing these fractions. So when I factor out that 1/10, all these like fraction pieces are going to disappear for us. That's just going to make the computation a little bit easier for us to work on. Now, ordinarily I would rewrite this, but I am short on board space, so I'm taking a shortcut. And hopefully that doesn't mess me up too much. So here we're going to get, okay, so that's a 1, so I don't need that, and I don't need that one either. Okay, so we end up with a negative 3x minus, turns to plus 4 root 3. So we end up with a negative 3 plus 4 root 3 x And then we have a negative 4 minus 3 root 3 for the y's. So we'll have plus a negative 4 minus 3 root 3 y. Then in the bottom, we're going to have a negative 3 root 3 minus 4 for the x. And then for the y, we have a negative 4 root 3 plus 3. And a 1/10 all the way out in front of that. So if I want to find the matrix that's going to induce this, right, something times the vector xy, just like we did in the last example from the last video, basically it's going to be these coefficients of the x's and y's. So the matrix that's going to induce this is going to have the negative 3 plus 4 root 3 in the top left, and then negative 4 minus 3 root 3 in the top right, and then this will be our second row. And of course it's all going to be over 10. So when I throw all of this together, I'm going to end up with a matrix that looks alike. Start it out this way. Let's put all the radical pieces second. So I'll have negative 3 plus 4 root 3 all over 10 for the first coordinate, and then negative 4 minus 3 root 3 all over 10 for the second coordinate. And then I'm going to pull up this one. So I'm just going to reverse the order so I'm consistent and my radicals are second. So I'm going to have negative 4 minus 3 root 3 over 10, and then 3 minus 4 root 3 all over 10. So this is going to be my matrix that induces this linear transformation. And if I wanted to do kind of a quick check, right, to make sure I got everything in the right place, I have this beast times x plus this beast times y. So that's what I have, the beast times x, and the other beast times y. Then here I have the bottom left times x, that will give me here, and then this one times y, that will give me here. So this is going to be our resulting matrix. So I wanted to do this example in this video because it kind of leads into the next one. So in this example, we did one linear transformation and then we followed it up with another one. So think back to what you used to do with like regular old functions, right? Sometimes you could take a function, you can work through that function, and then take the result and put it into another function. It has a very musical name. It's called composing functions, right? So that would be f of x, or f of g of x would mean throw x into g, and then take the result and throw that into f. So here we took a vector and we threw it into s, and then we took that result and we threw it into t. So we just found t composed with s. So in the next video, we'll be talking more about composing linear transformations and seeing if we can find some shortcuts, because this was kind of gnarly, and hopefully we can. So I hope you found this video helpful with reflections and rotations, and I'll see you in the next one for composing functions. Bye for now.